Good afternoon, May 17th, 2023. Well, we've been reading about this differential equations, and this is really just essentially an introductory text about the plane curves and their integral equations with regards to differential equations. Any function that's defined in terms of a function defined as a function of its own derivative, conversely integral in an integral form. And we got up to about the chapter 3 here, special types of integrating factor, that we're getting after quite a discussion about the linear fractional equation. And in this context, there's been setting x equals y and considering the identity function, a particular function, or a restriction of the domain to positive numbers, and thus that in a setting where x equals y is the identity function and one of our x or one of our y respectively is this inverse, that it works out that in either way x and y are interchangeable. And so it ends up, when you find a differential solution, that in a sense you can solve it for x or solve it for y and then replace every other instance of it with x or y. Thus that it makes some things just kind of trivial and some things kind of vacuous and some things kind of tenuous about some things that might be kind of central and special. And what that's been getting into is, for example, for this linear fractional equation, that it's a particular example where when it has the constant coordinates that make it reflect so that this x and y are interchangeable in these plane curves, that it ends up also being having indeterminate forms in some of the points, because the very coefficients that define it then have all the other things developed about it, about the usual. There's 4 different variables, parameters to the numerator and denominator, 2 functions that are linear in x and y apiece, that when they're all the same, so it works out their constant, and that way that x and y are, this function is also symmetrical as about x and y, that it ends up being quite an interesting thing. And then it comes with the vagaries of that, what would be indeterminate forms, or the ambiguities, which would lead to erroneous forms. But here, it also then is otherwise it kept in place and held up together because x equals y. And so it's only in this system of a framework of equations about which it's so defined that this identity function becomes the one dimension, the first 0th dimension, or what? The 0th dimension is a point, one dimension is a line. And then the idea is that this x equals y line in this first quadrant then makes the x and y kind of semi-dimensions. And the idea with these semi or demi dimensions is that then there'll be some interesting ways to frame out how to make it so that then there's integration of essentially above or below this diagonal through the space, and being able to consider the space as closed or compact or bounded, even though it goes to infinity, of course. And this non-standard approach is looking for interesting features of the numbers in this particular setting of what results a coordinate system of sorts. This identity inverse coordinate system, or this semi-dimensional product space, that then lots of other things that otherwise solve out and fall out for the, for example, this linear fractional equation about out of the origin, develop these tangents and normals and trajectories as about orbits in these plane curves. The parametric forms for the ellipse, or parametric forms for the oval, parametric forms for the circle, for example. And then also with regards to special things like the parabola and the integration of this function in one of the other dimensions, and how it works out then that closing the reflection about that is for making that then it's basically instead of 1/2 x squared, it works as a way to compute stuff out of about x squared, which makes pretty much good sense if you look at it and you say, oh, I've computed the area, like computing the area of a square, which is x squared, and you compute it underneath this, and it's, well, it's the integral of this y equals x, so it's x squared over 2, and you multiply that by 2, and you get back x squared. So that these kinds of checks trivially work out. That makes it possible to look at as a setting, as an n-set set, a way to put together some of these things that make it so that then there's to be arrived at results with some sense. Instead of, besides just, interesting things, the ideas come up with general forms and fundamental theorems of equations about in these spaces. But so far in this little book, which is at least 70 or 80 years old by now, and reflects the previous curriculum essentially. It's in terms of plane curves and their integral curves so far, compared to the modern curriculum, which is about differential equations, diffeqs, and their solutions, which are these plane curves in a sense, where they exist, like so that there are other solutions to differential equations depending on the equation of these things. But that the plane curves have, for particularly simple and usual plane curves, that they have particularly simple and usual integral equations, that these integral equations map many a usual kind of thing, and especially so when it works up that taking the little bit extra of this work to put together a sort of an integral and differential approach to mensuration or integration, it makes for just a trivial toy kind of an integration and an analysis. The mensuration as of different than the quadrature and different than well, I guess it's not so much different than Riemann and Lebesgue and Stieltjes, because it kind of works up elements that have been developed in that to develop these other elements, then to make their own kinds of equations and such. But then figuring that maybe then those could be established in different ways if they're independent, say. But the idea is to implement a kind of integration, and it's just kind of a toy, where a toy is not the same thing as a tool. Like a tool is basically this tool can affect this work, provides this advantage, and makes it possible to make this effect. And the toy is kind of like that also, because it starts as the effect, and it starts as the idea is that, well, it's a working toy, and besides that, if it falls apart, then it's just kind of imaginary or an effort. But then the idea for this kind of toy theory is to work up eventually what is a sort of system of particular things that make it so to work up things for mathematics, then to make, for example, what are corner cases or edge cases, where there's the happy case, which is for the sensible, fungible, and tractable, is where it's under usual best effort, not worst case terms, happy case, and that there's this generality of the tractability of it, and it falls under averages of those, whereas the edge cases are either contrived or pathological, or just happen to maximize the worst case for some algorithm of some data structure, is what computes and crunches out and computes these numbers or the products or the terms, and that the corner case is like an edge case with two edges that come together to make a corner. So that's just kind of like the last case that needs to be covered in a sense, or the edge cases and corner cases. So the idea is that for some things that are edge cases or corner cases to usual approach to the analysis, if you can find a toy that works from that corner on out instead, and you can frame it in that, or to give it a region for that, like, well, here in this metric we're going to solve it with this corner tool, and over in this metric we're going to solve it with the edge tool, and in all the field, meaning where all these tiles that are laid down in a sense in the field of laying of tiles, then we'll use the usual means. And then otherwise there's the idea that it can arrive at some particular neat identities that relate things that weren't otherwise identified, then that's mathematics. And then you can say, well, now I need to study all of mathematics and find out who in history already did this. Because by and large, almost certainly somebody already figured it out. But then that's one thing when you have access and availability of some of these non-standard tools, and for this analytical character, is some of the stuff people would just never even be able to conscientiously have they exist, and so rationally they wouldn't. And so for this, and this conscientiousness is basically for the rigorous formalist, the formalist who obeys rigor and demands for his scientific conscience that he cannot lie to himself or lie to others, or that his mathematics can be used to make not mathematics or the unmathematical. That is enabled when the non-standard has standard results, like direct delta, and it's a convention of formalism is built out and down and about how it is. Or the Jordan measure for the path integral, and it's like, well, we've got iota values and they do add up, and they are consistent, and with all of axiomatic descriptive set theory with its one relation that defines everything in model theory, which is for models of things that can be so related, for operator calculus above that. And then for the Dirichlet problem, then to figure out kind of how to do that for the Dirichlet function with the signal continuity, that these are the kinds of things that mathematical conscience demands. But then also when developing these kinds of just kind of excursions or whimsy, or this idée fixe that allows one to look at something as like, it's got to come through this curve looking like this kind of straight line, or this is the only kind of straight line I have to measure it against a straight line, so I need to figure out how it so orients that, when you put your thumb up to it to measure its form and proportion, it lines up. So these are the kinds of things that from the painter's perspective or the projective are to be things. So that philosophical bit aside, and it's for mathematically formal rigor, that it's also a symbolic statement and mathematically formal rigor in words that we're talking about. I'm just leafing through this book, and here's this tan phi and r d theta dr about this translation of coordinates and in and out of, about these plane curves and their coordinates, and about how I'm going to the polar coordinates from the gets to the orthogonal trajectories, about various cases, like x squared plus y squared minus 2ax equals 0. So we normally look at that as something like x squared plus minus 2ax plus y squared equals 0. Except you'd think of that as two monomials in x and y. X plus something and y plus something if it's going to factor and have roots. And when you think about things in these terms, they're roots, and trying to figure out what are solutions to this equation, and because as by itself it's just an expression that identifies constraints, that whatever the values of these variables are, they have to add up, so they make it like so for this expression to be true. And particularly then that these roots are as about equaling 0, that, well, it makes the additive identity, so if you can approach to that in the additive terms, it will hold so in the limit. Then these kinds of things is like, well, right in the middle, it actually works out that these roots aren't real, or they're not positive, or they're not, they're imaginary, not real, or they're negative and not positive, or they're off the line of this x equals y in one or the other of these places where it's not symmetrical about x equals y. Then the idea is to figure out how to make placeholders for that, which then have that following the rules of the arithmetic products that do fall back in the field, that these edge and corner cases can build out into the field. Find represents for varying A all circles which touch the y-axis at the origin, the center of any individual circle being A, 0. See, this is where you'd think of that if y is a constant, it would be one or the other. But here that it's just like all the circles. To find the equation of the orthogonal trajectories, replace dx by dy and dy by negative dx. So here we've been talking about the inverse of x and y as 1 over x and 1 over y, but here's another example of this inverse space. Replace dx by dy, okay, they're the same. And then replace dy by dx. Well, wait a second, we don't really have negative values here. but it would be dy by negative dy instead of dy by negative dx if they're still the same, and working up and down from this kind of place. X squared minus y squared quantity dy minus 2xy dx equals 0, which is really the same equation with x and y interchanged throughout. Except that the x squared minus y squared term is the same. And so you usually write this is this is the case for x squared minus 1, that it's x plus y, x minus y. And so then we get to where x plus y is 2x and x minus y is 0. You get this whole thing about that there's 0, and then there's x equals y, and then twice that. So that's pretty remarkable. That those would be the factors, the roots, that those multiply together and make back this identity function. This general integral, therefore, is x squared plus y squared minus 2 beta y equals 0. He has this method about the differentials to treat them algebraically and add them back in and multiply them back together and then cancel them back out. So that the orthogonal trajectories are all circles which touch the x-axis at the origin. So the orthogonal trajectories for these circles centered at A are the circles centered at the origin. And it would be so kind of for these circles everywhere, it kind of seems, about the orthogonal trajectories of a field of circles. Usually just think of the lattice as orthogonal everywhere, and any integer point or any rational point or Here it's so for circles anywhere. So carrying on, we've already looked at that, but looking at it again in this later learning, reapplied and this refined and put back through it, it makes either a case where, well, that's using something that you declared to prove itself, so it's invalid because you just stated you just restated what you declared, not that you've derived it from other things. Although you can establish that it's not inconsistent with other things, but it's something to be avoided. But then other times it's like taking these later developments, as long as they're independent of the developments when into an earlier thing, then you can look back at that as like, well, that expresses a fact about it, then I can use to build it back the other way. It's the origin of the complementary dual in the dialectic. Once you reach a certain place where you've established a theorem about something, it's reverse engineering it in a sense. Level lines and lines of slope on the surface. And this was this great thing about the gradient, about and the topography and the isoclines and the level lines. Making to illustrate possible modes, this is when we got into the linear fractional equation, making the usual substitutions. Now I'm not sure exactly why he says that y equals vx is the usual substitution, except that he is relating it by one factor of the line of sort. If v minus a and v minus beta are factors of the numerator, indeed, I'm not quite sure yet why v is the usual substitution. Will be particular solutions, and y equals ax, y equals beta x. Thus, among integral curves are two straight lines through the origin. And here it would be this 0 and 2x, it seems, known as the principal lines, and alpha beta, the principal directions. They are real and distinct, coincident or imaginary, according as ... That 0 and 2 are the roots of v squared minus alpha beta. Or rather, v squared minus 2abv minus alpha plus alpha beta. So carrying on in this manner is then, as I was interested about these points and these points in the descripting and about the family of ellipses encircling the singular point at the origin, which is their center and limiting point. And then also that being about the ellipses and what may be written about the linear fractional equation here, and here a special case that's sort of outside it, but that will be built up as of this identity function and the complementary dual and the complements in the duals. The integral curves ... are closed ovals. The origin is their limiting point or center. And that's about the constants, that the constants range through this line. There, and here in that particular element, it was like, well, and they can't be 0, or they can't be 1. If already, it's going to be kind of like dividing by 0 is like infinity. That treating this line as a solution is like a differential equation is like dividing by 0 is like infinity. Not dividing by 0 is undefined, thus stop. But the dividing by 0 is like multiplying by infinity. It's a thing in some models of the numbers. So we got reading in this equations of the higher degree. Oh, here's the bookmark. Equation may be satisfied. Let's see what we have here. Example 2. A geometrical problem sometimes leads to a differential equation whose singular integral furnishes a solution aimed at. Whose singular integral. So this is after discussion of the Clairaut equation, and the Clairaut equation again had this placement of this cumulative result, this kind of building that I need to write down and formalize and put in a thing. About the integral curve represents a singular solution of the equation. The equation of this curve in a form phi xy equals 0 involving no arbitrary constant. Since the envelope, and I'm not quite sure where it was defined, envelope of the primitive family is obtained by eliminating c between that equation and x plus f prime c equals 0. And since the result of this elimination is identical with that of eliminating p between x equals negative f prime of p and y equals negative p f prime of p plus fp, where here p was defined as y prime and x equals y, and x prime equals 1, or rather y prime equals 1, and that being dy dx, say, and also dx dy also equals 1. And so being that dx dy and dy dx equals 1 over this whole function makes it so that when it's just an extra constraint kind of added to any of these other functions, it holds all this other stuff in a square. And it makes all these other things that make for these assignments fair. And that is how it stays rigorously formal. By eliminating p, we obtain the equation of this curve in the form phi xy equals 0, because what we had was y equals negative p and then f prime of p. So f prime of p, if p was dy over dx, then f prime of that is 0. Y equals 0 plus fp. But that's in terms of x equals negative f prime p negative 1. So y equals negative 1. Here we don't have any negative numbers in this set or space, so it's kind of like when it's so applied for something like that, then that essentially makes, as a product term, kind of like a complex number. It's like, what's I squared? It's negative 1. Well, what happens when you apply this Clairaut's theorem to this bit? It makes a similar kind of thing. it follows that the singular solution may be interpreted geometrically as the envelope of the family of integral curves. Y equals px plus a over p, all right? Y equals x plus a equals 0. Differentiating dy dx equals dy dx plus x minus 0 over dy dx, and then dy dx over dx, or dy dx squared. And this was read again yesterday, and it built out how it arrives at the parabola. And it gives a second integral back out of it, though, dy dx squared, which is 0. And so 1 equals 1, always great, right? Plus x times 0. Or that, and then if that was going to be so, then there would need to be something that made it for so that it was the a over p squared, or this x minus a over p squared, this term, this part of the product, would have to be its reciprocal so that it equals 1. And so that instead of that going to 0, because it's a constant, well, you taking the derivative of a line, it's a constant. Take the derivative of that, it's 0. That the idea is that to build that up as in the integral equation above it, and then fall out from that what it could be. And this is not an unusual approach in a lot of different things. And then it adds more constraints that, again, we're adding constraint after constraint after constraint to this list until it results that there's any number of things that can be worked out from it, even if they only exist in 2 points, 0, 1, and oscillate back and forth. That this is, again, reading about this, how it was checked from reading the Clairaut equation, that for this x equals y, that putting in x equals y as the plane curve of interest, the identity function, that this is like so. Example 2, a geometrical problem sometimes leads to a differential equation whose singular integral furnishes the solution aimed at. For instance, to find a curve such that tangent at any point makes with the axes a triangle of constant area a squared. So we want a curve such that the tangent at any point makes with the axes a triangle of constant area a squared. So with the axes, so the tangent is you kind of take the tangent in this context is taking the tangent at the curve and then extending it all the way to the behind the axes. So where this curve is in the first quadrant, and the idea is that this curve is only ever it's positive and finite. Or I suppose if it's not, and if it's positive and finite, then the curve intersects y at a positive number and it intercepts x at a negative number. So the triangle related to the axes would be with negative x and y, and those intercepts of the line that by its parametric form, the tangent, its slope, as given that its parametric form is solved for that tangent being at that point on the curve. So to find that with the axes, a triangle of constant area A. So what is the area of a triangle? Is base times height over 2, and so that base times height over 2 is that where it intercepts y is the base, or the height rather, and where it intercepts x is the base. So we have a formula for the area, and then that basically requires that would have to be constant. Since the intercepts of the tangent at xy on the xy axes are x minus y over p, y minus p over x respectively, here, for example, where x equals y and p equals 1, that it's 0 and 0 respectively, the differential equation is x minus y over p, y minus px, or 0 times y minus px is 0, because y is equal to x and p is equal to 1 equals 2a squared. It's like, all I have is 0 times 0. It's an indeterminate form at best. Actually, it's 0. It's not an indeterminate form. It's just 0 times 0. Well, actually, it's 2a squared, which makes sense because a is also 0. Or y minus px quantity squared, which is 0, equals negative 2a squared p, which is 0. Well, that checks out, but it's not very informative. It's what we'd call trivial or vacuous, where the idea of trivial is that there's not much point to it, or it's uninformative, or something like that, or that it's just natural. Sometimes trivial just means natural. And then the vacuous is something that's like, it doesn't exist. It's like divided by 0. Whereas other times vacuous means it's over the entire space. It's as of a vacuum. And something occurred in a vacuum and immediately attenuated throughout the entire space. These are the kinds of things. So, this is equivalent to the Clairaut equation y equals px plus minus a root quantity negative 2p, or root of negative 2, which would be negative 2i, except that a equals 0. About figuring out, then what if we approach a in the limit as either way, approaching 0? Then what could be figured out, how to make it so that for this equation, there's these other things guaranteed to exist by how it would stand up in the middle as these products, so that it would be possible to figure out how it possible is this vanishing, and you can make a linearization of sorts in about as the linear fractional equation basically goes to the identity function, that it would have this when it's vanishing as a ratio. Or, for example, as an extension of the complex analysis, whose singular solution given parametrically by x equals plus minus, or minus plus, excuse me, a root quantity negative 1/2 p, and that being negative 1/2p as it's written, and y equals plus minus 1/2 a root negative 2p. But x and y are equal, so there's a sort of, and they're only positive, so x equals a root negative 1/2, and y equals 1/2 a root negative 2. Now this is kind of interesting because besides the one case where there's the line, it's like this is the line x equals or y equals 0, and then this is y equals x, and then this is y equals 2x. And so you can see in a sense that, well the one's kind of, it's got twice, its derivative is twice the other, so the area underneath it at any point is twice the other one. But then this point about where the derivative's 2, and the y equals 2x and y equals 1/2 x, is they're symmetrical in a sense about the this y equals x. In terms of functions that are perpendicular to y equals x, or x equals negative y, as it were, rather at that point, plus y, that y equals negative x plus y. That these are some interesting things that make for these families of plane curves that kind of walk up and out this identity, just like numbers go out from 0 to infinity. And that here, these whose singular solution is given parametrically by these two lines on either side about it, is xy equals 1/2 a squared. Though here, it's that would be x squared equals 1/2 x squared. So it's making a case for this vanishing case in the limit about this identity function and curve, where even this what otherwise a is 0 is about, well what happens when you divide it out? It's in a sense, divide it out and call it infinity. What's its middle of nowhere that it crosses to and it gets to the other side? What is it? Well, that's just its formula. X squared equals 1/2. Well, then I suppose that would have to be x over root 2 squared. The a is x over root 2. There. Thus that they're equal. Thus the curve sought is a rectangular hyperbola. A rectangular hyperbola. So now I'll go and consult later some aspect of studying the hyperbola, because I've really had a hard time understanding the hyperbola and the hyperbolic sine, hyperbolic cosine, and an arc hyperbolic sine and arc hyperbolic cosine. And there's sine and cosine and secant and cosecant, sure. And then there's hyperbolic sine and hyperbolic cosine. And then there's arc sine and arc cosine. And arc sine hyperbolic and arc cosine hyperbolic. And so these are the trigonometric functions. And then there's, of course, tangent, cotangent, and that apply to sine and cosine and secant and cosecant. But what I'm wondering about is a rectangular hyperbola. And so this is a family of these properties, these geometric objects that I need to relearn a bit. All right, now, so this is after Clairaut. So in this idea is I'm planning to stake out these developments and after this identity function semi-dimensionality, some analytic results that stake out and build out some things, so I can just make some standard and non-standard results that establish some uniqueness and existence results for some completeness that makes for systems that in their closures or completions have these results in the limits, ... they only exist in the non-standard, to make it so that they're standard. Generalization. The next section here is generalization, the D'Alembert equation. The Clairaut equation is a special case of the more general D'Alembert equation, also known as the Lagrange equation. Oh, well, now we're talking. Y equals xg of p plus f of p. In fact, it is so exceptional a case that will now be excluded by the stipulation that g of p is different from p. So y equals x of g of p, and so if it's different, then that's something, because here it would be the same, because g of p, because it would be, for y equals x, it's y equals x times 1, and so g of p is 1, but p is also 1, and f of p is, otherwise it would have to be anything different from that. Now, because now p is y prime, and so y prime equals 1. So f of p is equal to 0, which is nice, though. Differentiating with respect to x, we have p equals gp plus quantity xg prime p plus f prime p, quantity dp dx. And we already looked at the dp dx, where dp dx is dy dx, and but you could also write it as dx dy, in which case it would just end up being that term isn't necessarily 0, the constant, because it's just instead just moves the differential raw on the other side of the divisor bar algebraically, because x equals y and dx equals dy. Now, I wish I would have thought of that a little bit earlier, and I'll have to, think about it again if I ever reread this page. But here, P equals GP plus quantity xg prime P. So saying that f of P was 0, or the f prime of P, because otherwise that would not fall out and leave the x equals y, which is already excluded. But here in the middle, and middle of nowhere and left in. Since GP does not cancel out with P, dx dy, we cannot, or dy dx, we cannot have dp over dx equals 0 identically. It is here though. And therefore the general integral curve is not a straight line. Nevertheless, the equation gp minus p equals 0 may have real roots. If p equals m is one such root, dp dx will be 0, and 20.2 will be satisfied. Or it'll be 0, or as I've been figuring out a little bit here, because dy dx is a special case, that it's getting more special. The deeper it gets buried, the more in the middle of nowhere it is, and it builds a bigger nowhere land. There's a song about Nowhere Man in Nowhere Land, writing us all his nowhere songs to nobody. It's a pretty good song. If p equals m is one such root, dp over dx will be 0, and D'Alembert's Lagrange's form will be satisfied. Thus, among the integrals of the Lagrange equation, there may be some of the linear form y equals xg of m plus f of m, where m is any one of the real roots of gp minus p equals 0. Well, here that's all of them. They're all roots. It will be shown later that these are singular integrals and not merely special integrals of the equation. Well, see, then that's a remarkable concept. The idea is like, well, does it have any real roots? Is like, yeah, any real number is a root. Whoa, well, yeah, it just equals 0. Well, what good is that? It's like, well, you can approach to it from either side, and it's not so relevant that it has roots, because it has these other properties about these the differentials of these families of functions that approach to it. And here with the idea being this 1 over x tipped over is going to be the other half, this, or the hat coordinates of a sort, may be divided throughout by it and thus rewritten. Thus it is a linear equation for x if log phi of p equals the integral of dp over gp minus p. But if that's integral of 1, and well, if it's integral of 1 over x, then log phi of p will be pretty good, because that'd be just log phi would be as of the integral of 1 over x and such, which is its antiderivative. Phi of p is an integrating factor, and the general integral computes as 0 equals c minus integral of 0 d over 0 1 over dx. Or conversely, see, that's dy over dx squared minus c minus integral of 1 over dx cubed, because phi of p is e. Integral of e over dx cubed. And that's a remarkably strange way to write an integral, for sure. And it would depend on some other things. But the idea is to figure out if then that you just say, okay, well, that's done. The space was pulled in, so that just projects to 3 points on the outside of it geometrically, comes back, making this outside integral equation of a sort. Again, I'm making up terms loosely and freely because it's still an exercise, in studying just only the positive numbers and only the developments that go into integral calculus and only the logical attachments that there are to them as numbers in arithmetic, but then setting that aside because there's available all the power of the limit and the, for that matter, the integral calculus. But there's also being able to separate some things algebraically in terms of then the substitution of terms in algebraically. It's reduced, it's restricted to this one special case, that then these functions that build as outside it would have to be pulled back into that to make it so to keep it that they attain to it, while at the same time it's just that the solution in the middle sits there on its own. It's singular. That the identity function is singular. And it's only so trivial as to be that its roots are real roots is because it's f of 0 equals 0. Then is whether f of 0 equals 0, or that there's a function that's basically, that the function that makes that the roots of the function is multiplying by 0. That becomes a special function with a little bit more character than just fx equals 0 by itself. Why would you write fx equals 0 for x? Why do you have to exclude it all the time if it's used in lots of different places where things are not 0 and they're not infinite, so we don't divide by them or multiply them? Well, then that seems pretty great, that it's set up and set outside as its own kind of thing. So we've gotten a little ways into the D'Alembert equation. It is only exceptionally that the parameter can be eliminated and the general integral obtained as a single equation between x, y, and c. And so here it was c equals 0, basically. Taken together with the equation itself must be considered to furnish the general integral. Example, y equals x plus p squared minus 2/3 p squared. So that's 2/3 p cubed, squared or cubed. So that's y equals x plus 1 minus 2/3 p cubed, but if that's to also equals 1, because what that'll need to be then is that p, which is dy over dx. I know this is a quite contrived constraint. It's rather arbitrary, but that p squared equals 1 and 2/3 p cubed equals 1. How does that taking the derivative of those would hold it up for so? So it's like after you take the derivative of that, it's sort of a constant, and then it falls down. And so this involves operator calculus is sort of about that, saying, well, not only have I made this contrived, I've attached an operator to it and reformulated it and made it an implicit. But these are the kinds of things that would go into establishing a higher level order thing about it. This is of the above form, differentiating with respect to x. 1 equals 1 plus 2 minus 2 quantity dp dx. And so for that b equals 0 is that's when this dy over dx squared, it equals 0, because it's the derivative of a line. Its rate of change is 0. Or p minus 1, 0, 2p dp d over dx plus 1 equals 0. The alternatives are therefore p equals 1. Well, that's no surprise, I suppose. And 2p dp plus dx equals 0. So that would be 2 times 1, 2, and dp plus dx equals 0. Now that's always remarkable when you see something like that. Oh, why was this planar curves all tough? Because it says 2p dp is dy or dx or so, say, plus by itself dx equals 0. So we can say that's dy, I suppose, and then we'd have to find a common denominator and put and make it so that these terms, but still, like adding differentials is in different variables. Adding differentials in the same variables is addition. It's that simple. But that otherwise, I really have to understand how that defines then for this integral curve. It's like, now go back through the methods and build it back out and down how it does it. Anyways, here p equals 1. Substituting p equals 1 in the original equation, we find that y equals x plus 1/3. This solution will be set aside for the moment. So this is about that 1/3 bit, and well, in this constraint world, it is like so for only a second, because it's bent off from when it was y equals x. From the second alternative, we obtain p squared plus x equals c. And deducing y from the original equations, we may express the general integral as x equals c minus p squared. That being dy dx, dy squared over dx squared. Keep in mind that though p is a constant, it's still a function dy dx. So a lot of times when I've said that here that expression of the formula is like so, that it's formulaic, and so, but x, the integral equation for x is 1/2 x squared. It says under the parabola that computes the integral, and then y equals c minus 1/2 p squared. That they're both same, or rather that they're different, because that's the one on the 2/3 side. So this goes back to like having put these constraints and these implicits and there's reformulateds into it, and then having saying, oh, for formal rigor, you'd have to tent that back up to integral equations and bring it back down, and then have those be very contrived boundary conditions, and then it'd be possible to attain to them by some limit from where to where in the middle of nowhere, and it's a thing. Then these are the kind of ideas that go into making the space warp to get to where it's possible to have kind of come together. Well, I suppose I'll let the bookmark there, and reading about the D'Alemberts or Lagrange's equation, because then Lagrange, of course, is a real big deal in terms of all the time parameterized systems we've been talking about, from relativity and quantum mechanics and the path integral and all that kind of stuff. It's the thing. So hopefully what this will lead to will be some more interesting sorts of developments in terms of that for something like differential geometry and these mathematical bundles and vector physics. That's something else to get to. This 2-volume series about the relativistic mechanics of a very modern treatment of the 1970s or so, about the jet bundles and into the Lie algebras. The Lie algebras are very, very popular, and up into the special unitary groups and the special ordinary groups, SO and SU, those groups. And so then carrying on though, any mistakes are my own, of course, and this is a development, as it were, given the idea of a deconstructive account of an elementary account of this the linear curriculum, and the combined reference to different points in the curriculum, which help build a context to have a deconstructive account, which isn't just eliminative, but is actually just kind of reflective, is the idea then that arises from this book as an elementary account with a very rich attachment to well-known important tools of these functions and interesting things about them, and providing especially on rereading, a development of the toolkit of the differential equations and the integral equations. That said, any mistakes are my own, and it's easy to make any mistakes when you're trying to develop in the non-standard, or in this case, as of about the methods of implicits, or this reformulation, and these or the attachment of arbitrarily contrived to the conditions. Yet at the same time, when otherwise all mathematics has already been over this field a million times. Part of the goal of the mathematical conscience is correctness, but another part of it is completeness. And so in that sense, then sussing out where the alternative fits in the middle of this nowhere. When it's like, you can't divide by 0. Why not? Because it's in the middle of everything. Well, all right then. Well, then how can we make it contrived so that we can make a triangle and have it just be one corner of things, and then when necessary you can flip back and forth between 0 and infinity? Not very simply, and it's fraught with absence of definition. There are too many other vacuous and tenuous cases that don't have always trivial results. Everything else falls out. It's trivial, it's constant, it's trivial. There's a rule, it's trivial, which is great, and it's rulial, it's regular. There's it's decidable. That this is about the talk when there are models of otherwise these consistent systems that aren't complete, to make it possible that there's a standard and non-standard model. There's infinity, and then there's infinity plus 1. Or there's 0 and there's a number at all. You know? So these are the kinds of things, and then for these deconstructive accounts and this reconstructive account, is the idea to find these kind of subtle relations and about what would only then be possible to validate then by kind of a generation of a higher order apparatus. And the complementary duals and methods in these complementary duals, like symmetry, like continuity across boundaries, and these kinds of things. It really kind of then speaks to what you need is methods in analysis and complementary duals when you're trying to balance things, and when you're trying to see both sides of things for matters of projective and perspective together, which is pretty much descriptive. And again, leads to its own need for its own kind of declarative syntax. So, carrying on in this way, I imagine I'll pick up again this more tomorrow, and so I'm still have the same idea fix. That identity in its inverse, and here's was introduced earlier. Like, also there's all the curves with besides x, y equals x. There's y equals x plus y, each of those curves that cross that curve and a perpendicular and normal to it. That's its equation, y equals x plus y. And you might say, well, that's just 0 equals x. It's like, no, it's y equals negative x plus a constant that happens to be the same as y. Oh, so that you got to leave it back in the algebra, a placeholder for the application of the additive inverse. In so few words, yeah. So these are the kinds of things that then get into these parametrics and these forms, which are then get into more of these things like the idea fix is that there's positive numbers and there's positive numbers. They form a quadrant. And there's x equals y and y equals x, and it's the same function. And there are functions reflective about it. And defining x or y, they're variously in x or variously in y. And then there's all these factors that have to do with methods of linear analysis about division by 0, and it's not infinity. But there is a thing. And maybe it's just a plain infinity, if you happen to have one according to perspective and projection. It's only accessible via these means. So carrying on in this way, the idea fix is then, now let's go into all the great work of this elementary textbook, this introductory, that the author is doing his best to give you the most going into it in the most digestible form directly.
and expecting then that these are always going to be fundamentals that hold up and build out for all kinds of things. That then what happens is to then have this as a special case in the middle of nowhere, about that then when it comes to like this singular, well, if some of these other things hold true and you can draw a line through it, maybe it'll hold true. And ... for singularity theory and this original analysis. And not because but not just to be contrarian, but to be for the mathematically conscientious, that level of conscious and rigorous. For the mathematically conscientious, or someone who has a mathematical conscience, is a rigorous formalist, 24/7, 365, which means all the time. Well, all right then.